Okay, so this was in the neighborhood of 500 to 1. Now 2 decks. So first let's just do not try to worry about the special kinds here.
Well, the denominator would be now 104. Choose 5. I have 2 decks.
Okay.
So I guess in this case we have 4 suits and then 26 cards per suit. So maybe 26 choose 5.
4
And
times.
that quantity times 4.
Okay, and we're trying to compare this to what?
To 4 times 13 choose 5 over 52 choose 5.
Yeah, 4 cards of the same suit. So your intuition in the beginning said everything's just doubling in the choosing numbers.
Yeah.
So maybe this ratio is actually the same. Do you have any revised thoughts on this?
Well, let's see. It seems like the denominator is going up a lot here. 104 choose 5. And then that 26 choose 5 would be smaller compared to that. And then 13 choose 5 would be 52 choose 5.
Okay.
So it'll be less likely.
Although, interestingly, when we were just sampling on introducing this problem, we actually did get a flush. And a flush, we said, in a normal one-hand poker is about 500 to 1.
Yeah.
And that usually doesn't mean you have to wait 500 hands to see a flush.
Well,
No, it doesn't mean we have to wait 500 hands. It just means each time. So how long do we have to wait on average if it'd be 500 to 1? On average, how long do we have to wait?
Well, if you have...
Well, 500 would guarantee it. If you waited 500 hands.
Why would it guarantee it?
Well, in a perfect world, I guess, you should see it by 500.
That's not true.
Well, you'd be, I guess, likely to see it at 500.
So imagine flipping a coin. In 2 flips, are you guaranteed to see a heads?
No, but it's likely. Likely that you would see a head.
So how long do you think you'd have to wait on average to see a head?
Well, it's expected to be 2 flips.
Okay. So 2 flips on average is how long you have to wait. So if a flush is 1 out of 500 chance of happening, how long do you expect to have to wait on average?
500.
Okay. Are you guaranteed to see it in 500?
No.
No.
Are you guaranteed to see it in 1,000?
No,
No.
you could go on forever.
You could never see it, but on average it's going to take 500 times. That was here, roughly 500. We'll go back to it mathematically and calculate it exactly. Here we don't know exactly what this is. Now let's not calculate it exactly, but do you see if we're going to try to eliminate here with one deck it was actually pretty easy to eliminate the special ones, the straights. What about over here?
Well... So you'd have to eliminate the straight flushes. So again, you'd have 4 suits. So it'd be 4 suits, and then now you have more cards to choose from to make the flush. So it'd be 4 suits, and then but there would still be 10 possible combinations. So you have to
so there's 4 suits, 10 combinations.
But then
it seems to stay the same.
So for each of these 40, each card you use, there's an additional card that can be swapped with it, but it keeps the straight flush identical.
Okay.
So you have to multiply by, I'd say 32.
or
2 to the 5th.
2 to the 5th. So each flush, let's say 2, 3, 4, 5, 6, this can happen 32 ways. Because there's 2 2s, 2 3s, 2 4s, 2 5s, 2 6s. So it's actually not that hard to subtract those out either. But let's go to Mathematica and see.
Okay.
Let's compare these. Let's compare these two numbers and see what we get.